Assignment 11, 2.4, continuity and discontinuity. Your essential question. How do you define continuity and use it? So you're going to need to know the different types of continuity and discontinuity. We're going to go over that right now. So you have a bunch of definitions on page 46, which I'm going to be going over. And I'll draw a little picture to go with each one. So first type is removable discontinuity, which we've already talked about a couple sections ago. So this is basically, let me draw a little picture here. You have some function that happens to have a hole in it. Okay, and that's C. Where that hole is, it's L. Okay, so it could look like this, or it could also, which would mean that at C it's completely undefined. Or it could actually be defined at C, but maybe it's still got that hole in it. But maybe there's an actual, so here's your limit, but maybe there's an actual output up here. So we'll call that output f of C. Both of these are removable discontinuity, and as we said again, we could redefine f of C to make it continuous. We could say, okay, yeah, there is an actual output here. We could redefine it. To make it continuous at C. Alright, second type, which we've already talked about as well, is step discontinuity. So this one looks like a step, so if I graph it, so basically I'm going up at C, it basically steps and goes some other direction. Or same direction, but we've jumped up, okay? So f of C is actually defined up here, but it's not continuous. So anytime you want to think of continuity, think, you know, can I keep my pencil here? Do I need to pick my pencil up? Yeah, I do. Even here, I had to pick my pencil up, right? It's not continuous, it's discontinuous. Okay, so this means that there's no limit. If we have step discontinuity, we're not going to have a limit as x approaches C. And again, the reason for that is, you know, my limit as x approaches C from the left is going to be different than my limit as x approaches C from the right. So my right and left limits are not the same. So I cannot have a limit here. Okay? Infinite discontinuity. So this looks something like, let's say, let's put this here. approach some kind of an asymptote. Right? So there's no way these two values, as I approach C from the left and from the right, I'm approaching infinity. Right? So there is no limit there. So it's approaching or approaches a vertical asymptote. And as x approaches C, f of x gets very large. Right, if this is x and this is f of x. But we end up with no limit. Okay, and then our last option could be that, oh, my function is continuous, so it does not have discontinuity. But there are a couple options for continuous. Okay, so one of them is, your standard function. Oh, look at that function. It's beautiful. It's continuous at C. It gives me a limit. And that limit is whatever f of C is. Oh, it's so perfect. Okay, well, there's another one. Oops. Which is still continuous. Okay, so our other one looks like this. It's got a point on it. I'll put that point right now at C. And that's fine. This one's also going to have a limit. And that limit, again, will be whatever the value is if I plug C into our function. Right? So this is, again, f of x. And this is x. Well, we call this point right here a cusp. And I'll get into that in a couple of minutes. But we can say that f of C will equal the limit as x approaches C of f of x, and that's going to equal L. Okay, so your limit is basically your function evaluated when you plug C in. All right, let's define a few things. Continuity at a point. Okay, so how do we know if we're continuous at a specific point? Function f is continuous at the point x equals C if and only if the following are true. First of all, if I plug C in, it's defined. Okay, so we know that f of C exists. Let's see, I'll put a 1 there. Okay, so first of all, f of C exists. Second thing that needs to be true is that the limit as x approaches C of the function f of x has to exist. Now, what does this mean? Hopefully by now you realize that a limit can only exist if it is the same from both the left and the right. So that means that the limit as x approaches C from the right equals the limit as x approaches C from the left. From left and from right, as I approach C on the x-axis, those outputs need to be the same. And if they are, then the limit can exist. And then the last bit here is that the limit as x goes to C of f of x actually needs to be the same as the output when you plug C in. Okay, so whatever those two sides are approaching needs to be exactly the same as f of C. Let me draw a picture. To give you an idea, again, I'll just make it really simple. So at this point where C is, let's see, f of C exists, right? And it's equal to the limit. And the limit as I approach C from both the left and the right is the same. Okay, so all three of those are being met. Okay, so we can say that this equals limit. Continuity on an interval. So this is several points, right? Many points put all together. Function f is continuous over an interval if it is continuous at each point over that interval. So it has to be continuous at every single point, which means it will satisfy all three parts of the definition of continuity at a point at every single point within an interval. I told you we would go back and define what a cusp is. So a cusp is a sharp point or abrupt change in direction. So it looks, the one I drew before looked like this. So this is continuous, okay? So I can, draw my pencil or trace over it without picking up my pencil. But the problem is that it does not have a derivative. So think about if you drew a tangent line on this side and you drew a tangent line on that side, right? To kind of think about the derivative, right? The instantaneous rate of change. Well, the derivative anywhere on this side is going to be positive, right? That slope of that tangent line is going to be positive. And the slope of the tangent line on the other side is going to be negative. So it's not actually possible to take the derivative here, because anytime that you think of like drawing a tangent line to help estimate the derivative by taking the slope of that tangent line, right? You want to take a couple of points that are around that point at which you're trying to find the instantaneous rate of change. Okay? And if I do that, well, a tangent line here and a tangent line here are going to give me two different estimates, right? They're going to give me two different slopes. One's going to be positive, one's going to be negative. So we can say that for a cusp, it is continuous, but there's no derivative at the cusp point. Just as a refresher, I think I've already gone over this, but this basically says the limit as x approaches c from the left, right? X goes to c from the left, okay? So on the negative side of c. And then the limit as x approaches c from the right, f of x, right? X is going to c from the right, okay? Does that make sense? Hopefully. And let's just recall that L, which is the limit, as x goes to c of some function, only exists if and only if the limit as x approaches c from the right of that function is equal to the limit is equal to the limit as x goes to c from the left of that same function. Okay, so these all have to be equal. As we're approaching c from the left, as we're approaching it from the right, they both have to have the same output. Okay, and then our limit will actually exist. Let's do a couple of problems. I'm going to look at page 50. Let's start with number 2. So these problems on page 50 ask you to answer 3 questions. Okay, so state whether the graph illustrates a function that has a left and right, or has left and right limits at the marked value of x, so at a point, has a limit at the marked value of x, and is continuous at the marked value of x. If it is not continuous there, you need to explain why. So looking at example 2 for A, does it have a left limit as we head to 3? Yeah, there's some output here, right? And how about from the right? Is there a limit as we head towards 3 from the right? It appears so. So does it have a limit? So I guess at that point you have to ask yourself, does it have a limit from both left to right, and therefore there is a limit at x equals 3? And that is true, because A was true, B can then also be true. Okay, and then is it continuous at the marked value of x? If it is not continuous there, explain. So is it continuous? So in other words, can I put my pencil here and move and never have to pick up my pencil? No, there's a hole right there. And what do we call that? Well, that's called a removable discontinuity. You can say that it's not defined at x equals 3, so it is discontinuous. Okay, so your answer to number 2 could look something like this. A, it has left and right limits at x equals 3. B, it does have a limit at x equals 3, and you could explain because both the left and right limits exist. And then C, it's discontinuous because there is a removable discontinuity at x equals 3, or you could say it's undefined at x equals 3. All right, let's do another one of those, one that might be a little more tricky, but I doubt it. Number 6. So looking at 6 now, let's see. So this is where it gets a little bit tricky. You have to do the marked value of x, right? So this is 5, the marked value of x. Sometimes people get a little confused and they're looking over here because that's where the discontinuity is. So at x equals 5, are there left and right limits? Yes, there are. So is there a limit at x equals 5? Does that limit exist? Yes, it does, because both the left and the right limits exist. And is it continuous at x equals 5? Yes, it is. Okay, you can put your pencil down and not have to pick it up. Over here it's discontinuous, but that's not what they asked us. Okay, so just be careful with that. All right, and the last one I want to talk about with you is these problems. I think we'll look at number 14. Okay, so we're going to look at that. So let's read the directions here. You need to sketch a graph of a function that has the indicated features. So you're going to make up this graph. Okay, so there's really no right or wrong answer. I mean, as long as it has these features that it says. So for 14, it's got to have a value for f of -2, but it has no limit as x approaches -2. So that means it's defined at x equals -2. But what does it mean for it to have no limit as x approaches -2? Hopefully you're saying to yourself, well, that must mean that both the right and the left limits are different, right? They don't approach that same output value. Okay, so I'll draw a graph. We won't do 6 here. We just kind of talked about it. So let's do 14. So this is just my version. You draw your own version. But the key piece here is that at -2, it's defined, but it has no limit. Okay, so maybe I come at it from the left, I end up here. Maybe that's where, whatever this number is, let's call it possibly 1. That's going to be my output. That's where f of -2 is defined. But then as I come from the right, I get some other output, and it's an open circle. Okay, one last thing that we need to explore, and that is the greatest integer function. So the greatest integer function was a step function. Okay, it basically looks like steps. So when you're graphing, it might look like, let's see. Okay, so that's, imagine that on a graph. It's used a lot in like paying fees. So like maybe when you stay at a parking garage, probably not anymore, but back in the day when we actually had like telephone bills that were based on like, different charges for different distances that you called. But anyway, so this is what we call a greatest integer function. And you find this on your graphing calculator. You go to math. Then from there you go to num. And from there you go to int. So let me show you. I've got my Wabbit menu up here. Okay, hopefully we can see this. So you go to your math button. Then you want to go over here to num. And then number 5 is int. Oh, and I wanted to do that in y equals. So let me try that again. Oh, wait, let's clear that. Okay, y equals. This is good, we're just reviewing. So we're going to go to math, over to num, down to 5, plug in x, and then you can see what that looks like. Oh, look at all those steps. Okay, you're not going to need to use that many.